very much for the introduction, and thank you very much for giving me the opportunity to give this inaugural lecture. At this stage, it seems to be customary to thank all the people who've played a significant role in my career. I'm going to thank them, but not at the beginning. I'll do it throughout my talk and towards the end of the talk. So I'm going to launch straight into my presentation, which is Engineering Mathematics for a Greener Future. And there's an outline of my presentation here at the lower half of this slide. So I'll go through that very quickly. We have 6 sections. In the first section, I give a very rough description of my research area. In the second section, I'll explain why this is relevant to the environment. In the third section, I'll delve a bit deeper into the technical side and explain about modeling of thermoacoustic systems. Then I'm coordinating a large European project called Tango, so I'll tell you something about that in the 4th section. In the 5th section, I'll focus on what we are doing here at Keele within the Tango project, and then I'll finish off with conclusions and acknowledgements. Sorry. Can you all hear me? Super, thank you. Right, so description of my research area. The general research area of mine is sound and vibration, and the specific area within this is thermoacoustics. Now, what's thermoacoustics? Thermoacoustics is the study of the interaction between heat and sound. So if you have a heat source, like a flame, near an acoustic wave, the heat source affects the sound, the acoustic waves, and the acoustic waves may affect the heat released from the flame. And that kind of feedback or interaction phenomenon is what thermoacoustics is about. Right, I want to take this apart and sort of explain it in more detail. First, let's look at the phenomenon of a heat source producing a sound. So shown here is, in red, is a heat source. I will run this animation in a moment. And this heat source has an oscillating rate of heat release. It'll get sort of periodically hot and cold. When it's hot, the sort of fluid around it expands. When it cools, the fluid around it contracts. And this sort of periodic contraction and expansion produces a sound wave, as is shown in this video. So you can see the oscillating, oops, that was rather short. Right, so you can, it's every time I press this. Right, so I won't sort of use the pointer, otherwise I wreck the animation. The heat source expands and contracts, and in the process, it sort of pushes the fluid particles on either side, and then that sets up a wave, and a sound wave travels away from the heat source in either direction. So this animation shows how a fluctuating heat source can produce a sound wave in the one-dimensional case. Right. Hang on. Sorry, I've shown you the wrong animation here. Right, I'll start again. Right, so in the middle of this picture, we have a heat source with a fluctuating rate of heat release. When it's hot, when it's red, it's at its hottest, and when it's sort of pale, it's at its coolest. So that represents the fluctuating rate of heat release. As the heat source sort of cools and heats periodically, the fluid particles next to it also cool and heat periodically, and they get pushed out of the way. And this is the effect which produces a sound wave. And you should see waves traveling away from the heat source in either direction. Is that visible? Right, good. Okay, so this is the phenomenon of a heat source with fluctuating heat release producing a sound wave. This is a well-known phenomenon, and it's also mathematically well understood. For connoisseurs of mathematical equations, I've actually given the governing equation for this process, which is the wave equation for the sound pressure P, and on the right-hand side we have a source term in which you have the heat release. So in a case where there's no heat release, this term is here, and you just have the plain homogeneous wave equation. So the quantities in blue are the sound quantities. The quantities in red, like this Q, are the heat quantities, and they are kind of coupled by this equation. C is the speed of sound, and gamma and rho are just constants that are not very interesting for our purposes. Right, so that was the sort of first part of the feedback, heat release fluctuations producing a sound wave. And now I'll come to the other part, where we have a sound wave affecting a heat source. So in this animation, we have a sound wave coming from the left, hitting the heat source and traveling on. And you may think of that heat source as a flame where combustion takes place. So upstream of the flame, we have sort of unburned fluid that gets combusted in the red sort of rectangle and then flows out as combusted product. And if there's a lot of fluid entering the volume of the heat source, you get more combustion. So that's indicated by the bright red color of the heat source, and of the flame. And if you get a sort of minimum with little fluid passing through, you get a lower rate of combustion. So this animation shows how sound can affect fluctuation, can produce fluctuations in the heat release of a flame. At this stage, I'd like to acknowledge my PhD student, Nalini Mukherjee, who has provided these two animations. Right, the mathematical description for this phenomenon is a lot more difficult because the physics behind it is not known, and the whole process is complicated by other factors that I'll come on to later. So at this stage, I'll just say that the heat release, Q, is a function of the oscillating velocity, or the sound, particle velocity in a sound wave, and typically there's a time lag involved, which I've denoted by 2 here. So again, the red quantities are the heat quantities, the blue, the sound quantities, and F is some function, so this is a kind of generic way of putting it. F is some function that describes how the two are related, heat release and sound are related. Right, so if we put these two processes together, and they do occur together when you have a heat source in an acoustic resonator, because the heat source produces sound waves. In a resonator, the sound waves get reflected, come back, travel through the heat source, and you get this interaction. So if you put the two together, you get a feedback between heat release fluctuations and sound waves. And if they are phased accordingly, then one enhances the other. The heat release fluctuations enhance the sound amplitude, the sound waves enhance the oscillations of the rate of heat release. And this mutual enhancement of the fluctuations leads to sound waves with rising pressure amplitudes, and this is called a thermoacoustic instability. I've got a graph here showing the time history of such an instability. This is an old graph which I did as a PhD student, which I measured as a PhD student. It shows the oscillation as a function of time, and you can see initially the exponential increase. That's due to this feedback, but then other phenomena kick in which kind of limit the rate of growth, and eventually you get a limit cycle. Right, I've got a little demonstration which shows this in action, and I want to show you this now. So what we have here is a tube, just a glass tube, which you can think of it as an organ pipe. Inside is a wire grid, and I'm going to heat this wire grid, and when I stop heating, you will hear the thermoacoustic instability. Right, so let's do this. So, I'd just like to add at this stage, health and safety know about this. I've got the blessing of Chris Bromley to demonstrate this, and yeah, this is all above board. But perhaps at this stage I could sort of tell you a little story, something that really happened to me many years ago. I was still a PhD student at the time, and I was giving a demonstration, a bit like this, but bigger, at a building owned by British Gas. It was a large new building, and in the lecture theatre, was also very new, there were big non-smoking signs up. And I didn't take too much notice because I don't smoke. And I gave my presentation. I presented a demonstration like this with a bigger flame, which was running longer. And a few minutes after I'd finished, the fire alarm went off. And the whole building had to be evacuated, and even the fire brigade turned up. So let's hope this won't happen. Well, I'm pretty confident this won't happen today. Okay, so that was the demonstration. Yeah, this demonstration is called the Rijke tube, after a Dutch physicist, Rijke, who discovered this phenomenon in the 1850s. It's a nice sort of toy demonstration, but it's more than that. It's kind of, it explains the fundamental, or demonstrates the fundamental mechanism behind thermoacoustic instabilities in combustion systems, and it can be a serious problem in combustion systems. So if you have a thermoacoustic instability in a gas turbine engine or somewhere, if that instability occurs, you get these high amplitude pressure oscillations. That means there's a lot of sort of oscillating forces shaking the structure, and that can lead to structural damage. In some cases, catastrophic structural damage, in destroying large pieces of equipment and causing millions of pounds of damage. Right, where does this occur? Well, you might actually have one in your house. It occurs in domestic heating systems, and if yours makes an annoying kind of noise, this might be due to a thermoacoustic instability. It also occurs in rockets. In the early days of testing the F1 engines that were part of the Apollo program, 20 out of 44 tests failed, some of them catastrophically, because of a thermoacoustic instability. It also occurs in gas turbine engines, where you have a flame in a cavity, and potentially it can occur anywhere where you have a flame was more generally speaking, a heat source in a cavity. And I want to show a picture of the kind of damage that you can get. This is the turbine of a gas turbine engine, and upstream on the left was a combustion chamber that suffered a thermoacoustic instability. Some structural bits of the liner came loose, got swept downstream into the turbines, and that is the damage that was caused. So this row of turbine blades was shaved off altogether, and the subsequent 2 rows, as you can see, got badly damaged. Right, now, why is this relevant for the environment? Well, combustion is polluting, and the aim is to minimize pollution by combustion systems. And one culprit polluter is NOx. It's a nasty chemical which is responsible for things like acid rain and smog, and it's generally harmful to all living things. And the approach that is taken by designers of combustion systems is to use lean premixed flames. These are flames that are sort of where the fuel and the air is mixed before combustion. And lean means that there is a lot of air, more air than is needed for the combustion to sort of occur fully. So they use lean premixed flames and they burn at relatively low temperatures. With that approach, you can minimize the NOx production, but this comes at a cost, and the cost is an increased susceptibility to thermoacoustic instabilities. So the trouble is, the greener you want your engine to be, the more likely it is to fail due to a thermoacoustic instability. And the solution, this is where we researchers come in, is to research thermoacoustic instabilities so that we can understand them, and once we understand them, learn how to prevent them. Right, in this section, I want to say a bit more about how we model thermoacoustic systems. And I'm going to explain it with this generic combustion system, where we have, on the left here, you can think of this as a kind of mixing chamber, and on the right, the combustion chamber. So in the mixing chamber, we have supplies of air and fuel being injected. They get mixed, and then the mix passes through some orifice that divides the two chambers into the combustion chamber. The mixture travels to the flame surface. It travels through, at the surface, gets combusted, and then sort of travels out towards the exhaust. Right, so this is a kind of generic system, generic combustion system, and with this I want to highlight just the sort of essential physical features that occur. Well, first of all, excuse me. Right, so we have an acoustic resonator here, and if there are acoustic waves in here, they will affect the heat source, as we've seen a bit earlier in one of the animations that I've shown. But this is not the only process. Other things happen as well. For example, if you have an acoustic field in the mixing chamber, the pressure will oscillate, and that will modulate the flow of the air and or the flow of the fuel. And that means that the mix that arrives at the flame has a sort of varying composition. And that, again, makes the heat release rate oscillate, so, and then sound gets emitted yet again. So that's the second process. Then we get a vortex roll-up, where the flow sort of flows past the edge. This is the flame holder, by the way, which anchors the flame so the flame doesn't sort of shoot off. So at the edges of the flame holder, we get vortex shedding, which is in the flame area, and these vortices also change the surface area of the flame, and if the flame surface area changes, the rate of heat release changes. And then you get several other things like reactants in trains of not properly mixed, and they travel through the flame and then sort of get combusted spontaneously, so it's not a smooth process that creates sound. Or entropy waves, these are hotspots that travel through the system, hit some structural component, and then produce a sound wave. So there are all sorts of physical processes going on which complicate the picture and make it rather more complicated than this little demonstration with the Riker tube. Right, so this is what I'm dealing with. And in order to sort of make a significant amount of research, I have into this problem, I have set up a European network, a European-funded network called TANGO. And I want to tell you about that in the next section. Right, TANGO is an acronym. It stands for Thermoacoustic and Aeroacoustic Nonlinearities in Green Combustors with Orifice Structures. This is our logo, and it's funded by the European Commission. The total budget is 3.74 million euros. This is a project that I have set up myself, so I'm the coordinator, or rather Keele is the coordinating institution. And it's a 4-year project. It started in November 2012 and it'll finish in November 2016. And we have a project website, and I'll just show you that so you can see the people involved. So that's the project website, and I'll go to the people page. Right, here we have the scientists in charge, and I'll just scroll down. So these are all the sort of senior people, most of them supervising PhD students and young researchers, and also doing offering secondments and doing other sort of things. Then we have the fellow. Oh, sorry. Yeah, coming back to the senior people, you'll notice that there are quite a few women amongst there. And this is not a coincidence. When I set up this network, I deliberately tried to sort of make the female participation as big as possible. So when I set up this network, I headhunted for competent and talented women and tried to incorporate them into this project. And it's worked, so we have quite a few women in there, which is nice. These are the fellows coming up. So we have 14 at the moment. There's one more to be recruited. And then we have the Keele University team. You probably recognize these people, James Allman and Anne Budgeon, our financial officers. Then Steve DeCroo, he's the website officer. He actually sort of looks after this website and updates it when necessary. Then in the rest, we have Anne Diskin, Ian Rawlinson, and Donna Sumner, who is down here. Those three are looking after the contract side of Tango. Mark Pullinger is the European Research Funding Advisor. He gives us support as well. And last but not least, we have Mark Turner, who actually developed this website. I feel I have a great team that are supporting Tango, and I'm really pleased to be working with them all. At this point, I'd also like to mention a few people who are more in the background, but supporting me nevertheless. And this is the Faculty of Natural Sciences manager, Kelly Montana Williams, together with her team, Shirley Courthold and Michelle Dawson. And also, I get a lot of support from Ian Marr, the kind of coordinator of all matters technical in the School of Computing and Maths, and his team of three, that's Ash Leek, Tom Cooper, and Steve DeCroo. And again, I'm very glad I've got these people to support me. Right, so let's go back to my presentation. Yeah, I've just shown you the Keele team. And on this map, you can see where the partner organizations are located. So this is number 1, that's Keele. 2 is KTH, Stockholm. It's a kind of technical university in Stockholm. Number 3 is the Technical University of Munich. Number 4 is the Technical University of Eindhoven. And number 5 is actually in India, IIT Madras. So we have these 5 academic partners. And in addition, we have 4 industrial partners. And they are IFTA, that's a kind of thermoacoustics company. They specialize in monitoring and control of thermoacoustic instabilities in the Munich area. We have LMS, which has become part of Siemens. They are sort of a software company in Belgium. Ansaldo Energia, gas turbine producer in Italy, in Genoa. And Beckert in Assen in the Netherlands, who are producer of domestic heating systems. So these are the partners in Tango. They all have at least 1 PhD student to supervise. Some have 2. And then we also have a few more partners, or peripheral partners, that are not on this chart. Right. The research in Tango is divided up into 15 projects, or 15 research positions. Most of them are PhDs. There's 1 postdoc and 1 short-term sort of master's type project, but the rest are PhDs. And we have basically 3 different sort of scientific areas. One is aeroacoustics. We have 3 sort of work packages in there, and each circle stands for 1 task for 1 young researcher. So that's a PhD, that's a PhD, that's a PhD. The red circles are tasks in the work package on fundamental thermoacoustics, and then the green circles, all these, are tasks in the work package on applied thermoacoustics. And at Keele, we have 3 such projects. We have project 2.2. I'll say a bit more about that later. 2.5 and 3.3. Those 3 are Keele projects. And as you can see from this chart, they are all interlinked. They all collaborate. Yeah, it's a network in the truest sense of the word. Right, so we don't do just research, we do a few other things as well. We have project meetings twice a year. This is a photo of an early project meeting at the Technical University of Munich. We have workshops, again, twice a year. That picture was taken during the workshop at IIT Madras last February 2014. This was a workshop on experimental methods in thermoacoustics. This is the campus of IIT Madras, a real jungle, quite exciting place. And that big poster was advertising our workshop, and these 3 are fellows posing for the photograph. We also do outreach. We had a big outreach event last September at the Keele Hub, and here you see 2 fellows, Nalini and Muttalib, demonstrating to these school pupils. In this case, it's sort of demonstrating dropping a bait through a viscous liquid. There were several other demonstrations as well during that outreach event. We also have a Tango charity, and that's depicted in this picture on the bottom right. We managed to raise funds to provide sort of equipment for school children, for 600 school children. And when we were at IIT Madras for the workshop, we actually visited a poor, a sort of special school for underprivileged children and delivered those teaching aids. And this shows some of the local children and 2 of the fellows, Luke and Wei, interacting with the local children. Right. Now I want to go into some detail about the research that we do here at Keele within Tango. I've got 3 fellows. That's Nalini Mukherjee, Alessandra Bigonjari, and Ashwatin Surendran. And they all have their individual project within the network. And I'm going to go through these projects one by one. Right, I'll start with Nalini's project, which is studying a laboratory combustor with a laminar V flame. This part of the slide shows a kind of schematic view of the combustor. So what we have is we have a mixing chamber with air and fuel coming in and getting mixed, and that passes through this green tube, okay, up in the vertical direction. And in the center of this green tube, there's a rod, and that acts as a flame holder. So the flame sits at the top of this rod, and it's V-shaped. That's why it's called a V-flame. Okay, so this is the combustion system, and then the acoustic resonator is represented by a glass tube, which is marked in blue. That's a glass tube, and there's a traverse mechanism attached to it so that the relative position of the flame within the tube can be changed. So that's the setup, and in terms of instrumentation, there's a camera that takes videos, high-speed videos of the flame and its movements, and there's a microphone that records the pressure, and then this, those signals get passed to some signal processor for further analysis. Right, when Nalini moves the V flame within the tube, he observes a number of different states. So starting at the top, if the flame is at the top, it's stable, so no noise. If the flame is moved further down, he observes a low amplitude limit cycle. It's a kind of a sound that's not too unpleasant. Then there's a sort of a transition region where you don't know what exactly is happening. And then there's a region of a high amplitude limit cycle, which is really quite unpleasant when you hear it. It sounds a bit like a sort of electric drill, like that. And it's quite annoying. And yeah, the transition between the low amplitude and the high amplitude limit cycle, the system sort of jumps around between the two and doesn't really know what to do. So this picture shows the sort of states that are observed. Oh, and another thing that he observes is that if he moves the flame down, he passes through these states, but if he moves the flame back up again, the states are slightly different, so there's hysteresis going on as well. Right, here's a kind of a sample of the measurements taken during the high amplitude limit cycle. That shows the pressure time history. It's sort of mainly sinusoidal. This is the corresponding spectrum. That peak corresponds to the oscillations that you see, but you also see there are minor peaks at higher frequencies. And the flame does rather dramatic things. So these are snapshots taken during one cycle, and as you can see, it sort of deforms quite dramatically. These are very fresh measurements. They were only taken a month ago. And Bellini's aim is to kind of analyze these flame shapes, try to determine the heat release rate from them, from the shape, and then kind of link them to the pressure to see how the sound pressure and the behavior of the flame are related. So that's, in a nutshell, that's Nalini's project. Right, then we come to Alessandra's project, which is a bit more theoretical and focuses on the hysteresis behavior that has been observed by Nalini, and also, by the way, that's observed in other combustion systems. It's quite a common thing to observe hysteretical behavior in combustion systems. This shows the model configuration that Alessandra has. It's a tube with two ends, a cold section upstream, a hot section downstream. The two sections are divided by a flame, and we have sound waves on either side of the flame. And there's one parameter that's variable, and this is this script L, which indicates the flame position. And yeah, hysteresis is observed, and Alessandra's aim is to simulate that mathematically with what we call a Green's function approach. So let me explain that in a nutshell. The Green's function is an impulse response. So imagine you have this configuration, and you set up a tiny little impulse, a sort of a very short heat release impulse, and that creates a sound wave. And this sound wave, which is the response to this impulse, is called the Green's function, and it can be, for geometry like this, it can be calculated mathematically. So that's step one of the approach, and in step two, the actual heat release from the flame is simulated by a series of impulses, and yeah, I'll explain that better in the next slide. So, okay, here we have a single impulse in terms of Q at a time t1, and the response is 0 until t1. Nothing happens before the impulse, and then after that, the system oscillates in some way, as this is shown by the blue irregular curve. So that's the impulse response. It's Q times G. G is the impulse for some kind of normalized impulse. G is the response to some normalized impulse. Q1 times G is the response to exactly that impulse. Right, now if you have a sort of general time history for the heat release, like is indicated in this dotted curve, you can approximate this curve by a series of impulses. And knowing the response to each individual impulse, they can all be added up, and this is shown in this graph. So that's basically the idea behind the Green's function approach. Mathematically, it's often written as an integral equation, which we have here. The t dash corresponds to the t1, t2, t3, etc. That q of t dash corresponds to these q's, and g of t minus t dash corresponds to those Green's function in the sum. Okay, so how do we calculate the time histories from that? So first of all, we do it in a sort of step-by-step way. Let's take one point in time, solve this equation that gives us P of T, the pressure. From the acoustic pressure, it's easy to get the acoustic velocity. I'm not going to go into that. Just take it from me that it's easy to get that. And when we have the acoustic velocity, and if we know how the velocity and the heat release are related, we can calculate the heat release. And then go back to the beginning, take the next time step, plug in the Q, and so on. So going through that sort of loop, step by step, eventually gives us a time history over a long period of time, or long time span. And if we, at the same time, vary the parameter, in this case it was the position of the flame, we can recreate the hysteresis with this mathematical model. Right, the third project is Ashwati's project, which is about, it's a more applied project, this one. It's about a combustor with heat exchanger. This is the kind of setup that is found in domestic heating systems. Here is a picture of one with all these sort of casings stripped away. So imagine this is like a drinks can with lots of little holes in the wall, and there's a mixture of air and gas inside, which comes out through the holes, and then it's sort of lit up. So there are lots of little flames sitting on the outer surface of this drinks can. And so it's like this, and then wound around the drinks can, that's not shown in this photo, is a kind of a helix, of a tubular helix, which acts as a heat exchanger, and all that is then sort of encased in a bigger container. Yeah, so this is basically the sort of system that we are trying to model. And below we have the model configuration. So that's the flame, and there's the wall of the drinks can. That's the inside of the drinks can. Then we have a gap. Here we have the heat exchanger tubes, and a flow sort of flowing through the tubes, through the gaps in the tubes, will produce a flow with shed vortices. And we have a few open parameters that can be varied in this setup. That's this distance LF, which is the position of the flame. This distance LC, which is the length of this cavity. Yeah, I should have said there's a rigid end there. So the distance between the heat exchanger tubes and the end is LC, the cavity length, that can be varied. And we can also vary the flow velocity in our model. Right. Now, the flame acts as an acoustic source. It supplies acoustic energy. The heat exchanger tubes, with luck, act as an acoustic sink. And, well, they're likely to act as an acoustic sink, especially when they have sharp edges, because you get vortex shedding at these edges, and vortex shedding means loss of energy. At instability, you have a kind of a balance between the acoustic energy supply and the acoustic energy loss, and at instability, the energy supply is bigger than the loss. That's what makes the oscillation grow in amplitude. So the idea is what can we do to control this instability? And the thing we're going to do is to increase the acoustic energy loss. Increase it by manipulating the configuration, and I've already pointed out we have several parameters to play with. We can play with the cavity length, we can play with the heat source position, and we can play with the flow velocity. Right, and these four graphs down here show what happens when you increase the flow velocity. So let me just explain with the first graph. They're kind of this is a stability map. Along this axis, we have the cavity length. Along this axis, we have the heat source position. And where the parameters are sort of in this region, we get an instability. If they are in this region, we get a stability. This is for a low Mach number flow, very low Mach number flow. And as you can see, the region of instability is quite large. And it's not easy to find the right values for cavity length and flame position to get stability. But as we increase the Mach number here from 0.001 to 0.005, the unstable region becomes smaller, the stable region becomes larger, and that trend continues as the Mach number is increased even further. And here at a Mach number of only 0.02, that's just a bit bigger than walking speed. So it's not a very high speed flow. There's a large area of instability, which indicates that if you blow through the heat exchanger, through the tube with a high enough Mach number, you can actually turn an unstable setup into a stable setup. So that's the idea behind controlling an instability by manipulating the configuration. Right, so these are the 3 projects that we are doing here at Keele. And I'm now going to finish off with a last section on conclusions and acknowledgements. Right, I feel very lucky, really, and privileged that I have this position as a secure academic position, giving me the opportunity to do research and to do cutting-edge research. So I find the kind of detective work that's involved in doing cutting-edge research very exciting and stimulating. Also, it's research with a purpose. It has a positive impact on people and the environment. It brings me in contact with colleagues from various different scientific disciplines, and I find that very stimulating. I enjoy sort of guiding young researchers. They bring their own ideas, and combined with my ideas, you get some really good work done, very productive work done. I have the opportunity to travel to many different countries and get contact with many different cultures. So, as I've said, yeah, I'm really happy in that position, and I value it very much. And now I would like to finish by acknowledging the people who helped me to get there, and that was of more or less historical order. Professor Ingo Müller, who was a professor at the Technical University of Berlin, one of my undergraduate teachers, he taught me the foundations of fluid dynamics and thermodynamics, and I'm still benefiting from that now. My PhD supervisor, Sean Fawkes-Williams in Cambridge, who was very inspiring, came up with loads and loads of ideas. And then listed here are 3 Keele people. Peter Jones is my mentor, so whenever I'm stuck and get into a difficult situation, I don't know how to handle it, I turn to Peter, and he normally sees a way out. And then there is Graham Williams, who supported my application. He's actually written the supporting statement for my application to promotion to professor. And Pauline Weston, the former Epsom manager, has also supported me there. And last but not least, I would like to thank my husband, William. William has always been there for me, and I value that more than I can express in words. And with that, I want to thank you for your attention and for coming to this lecture. Thank you very much.